Hello everyone. In this lecture, we will learn a fundamental concept in computer networks called reliable data transfer. And if there was a top 10 list of the most important problems in the area of communications and networking, I would say reliable data transfer would be the top one. As you are diving into deeper in learning computer networking, you will find out that reliable data transfer is rooted in many design principles at every network layers, from application to transport, from routing to queuing and scheduling. So in this lecture, we will first go through the very basic idea of reliable data transfer, in short for RDT, and how it is being implemented at the transport layer, where we will also introduce some very good examples of using the principle of RDT, such as TCP congestion control. So the main theories you will learn from this lecture include the understanding of basic idea behind RDT and the two examples that implement RDT called congestion control and flow control. So these two algorithms that pave the ground of internet and most of the communication networks. We will also learn a key mechanism called AIMD, which is the core idea behind congestion control and the internet. So last, we will analyze the performance of TCP in wireless network in terms of how reliable it is. And the practical works in this lecture include some exercises which you can download from Moodle and that helps you understand the RDT. And there's also a live demo that shows how RDT works in an open source discrete event simulator based on Python. And these demos will be illustrated in our face-to-face seminar in class. So first, let's look at a very interesting project from NASA called the Space Internet, where scientists try to copy the internet on the Earth into the space, and hopefully in the future, when devices like humans on different planets, they can communicate to each other. So the idea of building a similar internet in the space is very similar with the one we are currently using. There will be IP packets passing through every OSI layers, also called TCP/IP stack. So usually, if we send a high definition image from Mars back to the Earth, it will take around 30 minutes, provided that all the bits are transferred successfully without errors, without loss. Well, if there is a loss or bit errors happened, the packet will need to be retransmitted again, and it takes longer time for the next transmission. And this is caused by the congestion control in TCP in order to ensure reliable data transfer, which we will learn later in this lecture. So in brief, the biggest challenge in wireless communications for such space internet is the extremely long communication distance, which causes challenge to design a reliable data transfer. And a second example is video streaming over mobile network. This is a screenshot of my own mobile phone where I was watching a video on YouTube using my home Wi-Fi. And inside the YouTube player client, we can configure the quality as automatic. So which means it will play out a video that best matches your network condition so that you can view the video smoothly. So now let's say when the bandwidth drops, it's quite common in the public network. Now, folks, and sometimes due to mobility, right? So here I switched to on my mobile from switched off my Wi-Fi and switch on the cellular, which has a lower download data rate than my Wi-Fi. And then to further make the network even worse, I put my mobile inside my washing machine. As you can see, it's surrounded by metal surface inside, so I assume the signal is getting really poor. So the YouTube will do is it will automatically switch the quality from 720p to 480p. And this is also an example at application layer, where streaming protocol they can detect any changes in the networking conditions and adapt the select appropriate video bitrate in order to match the network. And the target is to ensure reliable data transfer. By data transfer, in this case, we mean we are referring to the video streaming. So you can try it yourself in your home with simply you can with YouTube on your mobile device. And the key technology behind it's called adaptive video streaming. There are two popular protocols in the market. One is MPEG-Dash, which is used by YouTube and Netflix, and the other option is HTTP live streaming, or HLS, where all Apple devices are using it for video streaming, like Apple TV or FaceTime. Okay. So reliable data transfer is a huge topic, and it is impossible to cover it in every application and at every OSI layers in one course. So in this lecture, we will focus on designing an RDT-friendly protocol at transport layer. Now, a great way to understand RDT is an example of the two generals problem. So imagine there are two generals that are separated by a castle in the middle where the enemies stay inside. And the two generals, they need to communicate to coordinate their actions. And obviously there's no mobile phone. And all they can do is to writing and replying through handwriting letters, which are delivered by a postman. Now, unfortunately, this postman they must go through a valley where enemies occupied, and there is a chance that the message could be lost or corrupted maliciously. A challenging question for each general is that how can they ensure their message will be delivered successfully? Well, a simple way is to send acknowledgement for every reply. But what if this acknowledgement lost again? Well, we can send another acknowledgement to acknowledge the previous reply, but this acknowledgement letter could be in endless loop in order to have. That's very difficult to ensure 100% reliability. Well, such two general problem is a typical communication model in wireless communications, where two computing systems attempt to reach out with each other by sending and replying message over an unreliable link. In computer network, we rather trust mathematics that there is a good probability that by retransmission, by acknowledgement, a message will be, we assume message will be delivered in a good way. Well, however, we should clearly know that we can never achieve a state consistency between these endpoints. This is because the communication conditions are maintained and updated by these discrete messages in different systems. So we first look at the service model that will help us design a reliable communication system. So what does reliable mean? It means that the data will arrive should be exactly the same with what it was sent, right? So here we present a service model offered by transport layer to the application layer. And the application layer includes two apps, two programs. One is sending application, the other is a receiving application. And at the transport layer, it maintains four different functions. The RDT send, which will called by the upper layer application, and the deliver data. So once all the data is arrived and successfully acknowledged, it will deliver it back to the upper layer application as well. And the UDT send and the RDT receive, they are the core in the transport layer to sending and receiving and coordinating a reliable data transfer, which we will cover in details in the next slides. And also note that both the sender, apologize, so there are actually 6 different functions at the transport layer, not 4. And note that both the sender at the transport layer and the receiver, the sender at the transport layer also have a receiving function. This is to receive the acknowledgement. And the receiver side at the transport layer also have a send function, UDT send, in order to send out an acknowledgement. So both sender and the receiver, they have is exactly the same roles: sending data, receiving acknowledgement, sending acknowledgement, and receiving data. So with a reliable channel, so everything will be perfect. We don't need to worry about the necessary to retransmit. Now, if with a unreliable channel, so which is the practice, so in this channel it will cause packet loss, the packet errors. So the main responsibility of RDT model is to ensure no matter how unreliable channel is, the upper layer communication protocol can have a very effective mechanism to ensure data is delivered accurately and on time. Okay. So normally we use the finite state machines to describe these operations and at sender and receiver, and later you will find out the state machines is extremely useful, in particularly when we program the communication protocol in code. Okay. So we first look at the most simplest version of RDT. We call it RDT 1.0, and gradually when we improve the performance RDT, we will increase the version number. So in RDT version 1.0, so both sender and the receiver have one state. The state here means it's the finite state machine. So the sending side of the RDT simply accepts the data from upper layer, from the application, and it will create a packet containing the payload data. It could be an image or video or voice, and send the packet over to the channel. And on the receiver side, the RDT protocol will receive the packet from the underlying channel through the RDT RCV function here. And then if it will remove the data from the packet, extract the payload data out and passes the data up to the upper layer application. And in this version, so there's no need for the receiver side to provide any feedback to the sender because it assumes that this is a perfect channel. There's no bit error, there's no packet loss. Okay. So this, but the question here is, this is too ideal, right? And what if there is packet errors? What if packet loss happened? So this mode obviously will cannot work anymore, and we will try to improve the version 1.0 to address those challenges. And also, I'd like to raise an open question here. What if the sending rate is faster than the receiving? Will this RT 1.0 work or not? So you can leave this question, and you should be find the answer after we introduce the flow control in the very end. And also in the seminar, we will show a demonstration how we can implement RDT 1.0 in the Python code. So RDT 1.0 is not a realistic one. It's too ideal. Now let's consider a more real channel where the bits in the packet could be corrupted. Normally, it's from 1 will be converted to 0, and from 0 flip to 1. Okay, and we assume that because for communications it's a bidirectional. Let's assume such corruption only happened first on the data from the sender to receiver, but not from the not for the acknowledgement, which is a direction from receiver to the sender. And but don't worry, we will get to that complex situation where both direction will corrupt the channel later. Let's starting from the simple case, and we still assume that all the packets are received, which means there are no packet loss. Okay. Now, since the sender and receiver they are normally in different places, let's say thousands of miles away, and the only way for the sender to have receiver's view of the world is to ask the receiver give some feedback. Okay, so in RDT 2.0, the sender has two states. So on the left state, the sender will keep waiting for any input data from the application. So if there's data, it will create a packet using by calling the make packet function, and it will sending the pushed data to the channel using UDT send at the transport layer. So recall that this UDT send function is locates at the transport layer. And then the sender will switch to the next state, which is waiting for an acknowledgement or a negative acknowledgement. And if a sender receive a packet, and if this packet is a non-acknowledgement packet, it will resend, which means there is error. So the receiver is expecting a retransmission of a correct packet. Now, if this is so in practice, this will be implemented as an if-else clause in the code, right? So if this clause, if this condition is not true, so which means it's a successful acknowledgement, so the sender will switch back to the left state, which waiting for the call, which waiting for the new packet for the next data, and in the loop. So by simply decide which state the sender should be in, so we can have a reliable sender. Now let's look at the receiver. So the receiver have one state, but have also need to determine when to switch the state. So if the receiver receive a packet and if it's corrupted, because it has mechanism to detect errors, it will send a NUC, which is means okay, the packet is corrupted, so please send me a new one, and it will stay in the same state. If it's not corrupted, then everything perfect. It will extract the payload data, deliver it to the upper layer, and send acknowledgement back. So we should, and hopefully this makes sense to you that by using the state machines, the two states in sender and one state in receiver, we can design a reliable data transfer. By reliable here, it's not that reliable, but somehow we can ensure if a data from sender to a receiver is corrupted, we have a way to recover it. Okay, and also an interesting aspect here is that now at the sender, after sending a data, does it send in the next one immediately or not? So answer is not. It will stop and waiting for acknowledgement or a negative acknowledgement and send to next. And because of this feature, this RDT version 2.0 is also called a stop and wait protocol. Okay, so can you find a problem in RDT 2.0? You may want to pause the video and think about the answer. Okay, so what if because in RDT v.0 we assume the channel is perfect for the acknowledgement data transmission from receiver to the sender. What if the backwards channel is not perfect? What if the acknowledgement is corrupted? How can we fix that issues? How can we further improve the level of reliability? And again, in the demo in the seminar class, we will also show how RDT 2.0 can be implemented in Python. So now the way to improve the RDT 2.1 is called RDT 2.2. Now, then the sender will be now in RDT 2.0. So the sender, sorry, it's a wrong slide here. Let's see how we can improve the corrupted acknowledgement issues. So in RDT 2.0, the sender and the receiver relies on the feedback to proceed to switch the different states. Now, what if the feedback is corrupted? And the sender will be confused between the acknowledgements and the negative acknowledgement between ACK and NUC. Because they have the value is 0 and 1. We have no idea which is the original inside this acknowledgement or negative acknowledgement. We may think of different ways to solve it. A natural way is we can use another feedback to verify this corrupted message. But the problem is this new feedback may also get corrupted, and there we are facing an infinite feedback loop. Another way is we can add a checksum to allow the sender detect and recover the bit errors, but it will make the implementation more complicated. Also, at the sender, it assumes that it knows that the bits are corrupted. It does not care if it receives acknowledgement or not, and every time it just simply resend the current data. But if there was a corruption happen, then this solution is perfect. But if there was no corruption, then unlikely the sender will send some duplicate packets. So if we can find a way to solve the duplicate problem, so this may work, and the popular way is to add a sequence number for each packet. So this is a extremely important new feature in RDT 2.1. So let's start from the sender. So here in this case, the sender have 4 states. Let's start from the top left, which is the beginning. So similar with the previous version 2.0, the sender will wait for data from the upper layer, and it will create a packet, send it to the channel, and switch to the next state. Now here, the sender will do a determination to see if it receives a packet, receives acknowledgement from the receiver. If this message, if this feedback is either corrupted or it's a NUC, which means it's an error, then it will stay in the same state and resend the packet. If not, it will switch to the next state, that is waiting for new data. So in standard, this wait for call 0 from above and wait for call 1 above, they are very similar. So they are just they both state will take new data from application and send out. The difference is they have a different sequence number, 1 for 0 and 1 for 1, another for 1. And if the new packet will be given a sequence number 1, it's created and pushed to the channel, the sender will stay in the state that waiting for acknowledgement of the packet with sequence number 1. So when you look at the sender, you can draw a line here, and on above, it's about sending and receiving packet with sequence number 0. And in the below, it's about sending and receiving packets with sequence number 1. And they are switching in the loop. So in this way, even though the packet is the acknowledgement is corrupted, we can still ensure that the communication, the transmission can be the failure transmission can be recovered. Okay, so the key to and at the receiver side, it has one additional state because apparently we need to wait for either sequence number 0 or sequence number 1, and the two states, they operate very similarly, except one is to determine if sequence 0 was successfully delivered, or sequence packet with sequence 1 was received successfully. Okay, so you can go into detail or reading the textbooks to make sure you're familiar with the state transition in the receiver. And I'm not going to details in introducing this. So in brief, the key to understand this protocol is that the sender will send in packet with sequence number 0 and sequence number 1 alternatively. So this is the most important features. Okay. And in practice, we can simplify this protocol by removing the NUC. So here each state is looking at for both the AC key and the NA key. Now here we can remove NUC by simplifying doing the exactly same job. Okay, so both sender and receiver, they are have a very similar design. The main difference is that at the receiver, when we generate an acknowledgement packet, we will add an additional parameter to indicate whether it's positive or negative. As you can see, I highlight here. If it's acknowledgement number is 0 or it's 1, to have the same effect of the ACK and the NAK. Okay, so you can read the textbooks by Curio's computer network book to try to practice yourself to verify how this works. It's nearly the same with RDT 2.1. Okay. All right. So far we have we assume we have gradually improved our channel. It's getting it more reliable. We can well handle the packet error, the bit error at the sending direction and at the feedback direction. But we still ignore one very important scenario, in particularly happened in wireless network, which is the loss. So there are many ways to detect and recover the lost packet. We can either do it at the sender side or the receiver side. And in this lecture, we look at the mechanism at the sender. So let's look at the state machines at the sender in reliable version 3. So version 3, we are dealing with the problem of both loss and packet error. So which we extend the functionality of 2.2 with the way to handle loss. So the sender has 4 states as well. At the beginning, it will wait for a call 0, which is the sequence number of the packet, and it will create a packet, send it. The difference is the new thing is there is a new feature called timer. It after it's sending, it will sending the packet. The sender will initiate a timer. So this timer is a counter in program, and if the timer expires, after the timer expires, if the sender still didn't receive an acknowledgement, it assumes that the packet is lost. It will retransmit. So this timer is how we dealing with packet loss. And after sending out the message 0, the sender will switch to the next state, waiting for this acknowledgement. And it will also, same with RDT 2.2, it will check if it's corrupted or not. And one additional thing is timeout. If it's timeout, it will send in the data and restart the timer. Now, if not, the sender will switch to a next new state, waiting for a new packet from the sender. Okay, if everything goes well, and then back to the next state related to this one that waiting for acknowledgement of sequence number 1. Okay, so a quick question here is, how can we determine the waiting time? How long should we wait? And because this is the value we need to determine, we need to decide in the communication system. And the value, what if the value you are setting to the system is too long or too short, what could be the problem? So you can think about this, and we will cover later how international standard, how they recommend to calculate this waiting time or the timeout value. Okay. Okay, so there is a link that there is an animation tool, so help you understand how RDT 3.0 work. You can go to the link and to see to help you better understand. And also in the seminar, we will do a demo of a Python code that implements RDT 3.0. Okay, so in brief, RDT 3.0 one last thing is we covered the sender of RDT 3.0, but we didn't give the receiver. So this is a task that you can try yourself. Can you do the receiver? Can you design the state machines for the receiver in RDT 3.0? Okay. So you should surprise yourself that it is the same with the state machine in RDT 2.1 or 2.2, and you can think about why. Okay. So now we have spent quite a lot of time to improve RDT and the level of reliability. Now, and we seem to have a perfect version of 3.0. But let's look at the performance issues. Assuming we have sender and receiver, they communicate over satellite link, for example, the Starlink one, and where satellites is the relay in between. If the sender is sending a packet of 1000 bytes, and let's assume the transmission rate at the sender is 100 megabits per second, and assume the round trip time is 100 milliseconds. If we use the RDT 3.0, which is obviously a stop and wait protocol, because every time after sending out message, the sender will wait for acknowledgement. Okay. Now we may wondering how efficient this protocol is, or in other way, we can calculate what is the utilization rate at the senders. So we can define the utilization as a fraction of time of how long the sender is busy in sending the data. So we can calculate first how long it needed for the sender to send out the whole packet, which is 0.8 milliseconds, and the time needed for, which is the propagation latency for the whole packet to arrive for a single direction, which is half of the round trip time and 50 milliseconds. And the time needed for the acknowledgement is the same for 50 milliseconds. We assume they are equally to simplify the situation. So therefore, we can calculate that the utilization rate at the sender is the sender is only sending data for a duration of 0.8 milliseconds during the total time, which is 100.8 milliseconds. And you can see the utilization rate is really low. Okay, so the reason here, because it is stop and wait. So unless the acknowledgement is well received, it do nothing. It just keep waiting. Okay. So how can you think of any solution to improve it? So you can pause the video, and then we will go to the next topic.